Thanks for speaking and take it away.
Yeah. Thank you very much for the invitation. Thank you very much for the opportunity to share about, I guess, my research and a little bit to those people who didn't heard my talks about flexibility to introduce like to flexibility point of view. And so let me kind of start from the kind of philosophy of like flexibility versus rigidity. When we talk about the rigidity, we usually kind of talking about that if we know something, then something else cannot happen. Or like in dynamic systems, say if you know some relations or on, not some relation, like maybe some equalities between some invariants, you know that only a specific type of object can have it. So you kind of have even like more like a geometric like classification even. So flexibility kind of on the other side stands the way that you more or less want to say whatever is allowed is actually possible. And this allowed kind of a little bit might be like a little bit of a shady zone in a sense, like what do you mean by this? But kind of along the process, when you study systems, you kind of learning something. And at each moment you can ask yourself, is it like everything what you know about, say, those quantities or no? So it's kind of roughly, if you think about, if you want to formulate flexibility question, what you do in kind of you're saying, okay, I want to consider you pick some class of dynamical systems. And then you ask yourself, okay, I want to look at those particular invariants. So you kind of pick invariants. I mean, I'm saying invariants like more data calculation, but you also can say about maybe some properties, like system having some collection of properties in the setting. And then you can say, ask kind of what is known. Okay, roughly say like if say invariance, you can ask, okay, maybe that quantity only can be smaller than the other quantity and never in the other order if you're working in this particular class. So we kind of a priori know that information. So let me maybe smaller and then come back. And then you can ask, okay, it's known. You ask, oh, is everything possible to realize? Is everything possible to realize? Okay. Okay, everything, I mean, up to what is known, obviously. And if you say yes, then this basically, you say that you got a flexibility result. So more or less, if you want to say, okay, so the flexibility problem, you kind of just follow this line and you got some result in that way. Okay, but assume you're having trouble to do that. And actually, okay, there might be two reasons. One, you didn't figure out how to realize some of the quantities. But then you can try to think that, no, not everything is actually possible in this allowed list because I found new relations. Okay, you found new relations. Okay, my writing is not super good here. New relation. Maybe one, maybe more than one. And what you do, okay, you kind of go back. You add it to what is known, right? Now you know a little bit more. And you can go back in a second, again, ask the question and get a flexibility result. Okay, where there is rigidity, most likely your rigidity somewhere in this. Possible that something particular stuff, what rigidity would be like, that particular relation only happens for specific systems. So, and there you can extract this like rigidity part of the result. So, in kind of in both ways, wherever you go, you kind of in a win-win situation. So you get a result. Okay, so if we kind of globally talk about kind of the tools, this becomes a little trick. So generally what we know like small perturbations, but small perturbation don't affect the systems as much, and also kind of like the quantities don't affect as much, and or usually kind of we are like in a critical situation, so we kind of have abstractions to do some of the stuff. So if you want to realize a lot of values, what you need to do, you need to do large perturbations. And then keep in mind that when you're doing that, you're like preserving all necessary properties, or you're able to preserve the necessary properties. Or other option, like what you could do is, so those are maybe more like explicit one, constructive tools, or you can have maybe some more general existing results. So, and obviously then you need to build like why for the specific, like, I don't know, numbers, something like there exist, but maybe you not explicitly build the system with those properties. Okay, so this is kind of like more a general theory of kind of how you could think, how you approach. So for today is like I wrote like entitled flexibility ideas for geodesic flow. So I'll try to talk a little bit about like what's done for geodesic flows, and maybe also bring up like what potentially could be asked, and where we don't know all the kind of like these relations. And most is known like in dimension 2, and and it will be clear later like that we know actually much more in dimension 2 about the relations. So let me set it up like the problem, so like talk about what class we're working with, what quantities we're looking at, and so on. So we take a connected, compact, orientable, two-dimensional manifold, smooth manifold, or surface. Okay, what we know that if we're working with this class of objects, that actually Poincaré classification theorem tells us what it can be, right? So Poincaré classification tells us that M is homeomorphic to exactly one of the following. Okay, what it is? Okay, it can be the sphere, and this is an object with genus equal to 0, right? It can be the torus, which is correspond to genus equal to 1. And it can be the connected sum of capital G greater or equal than 2 tori. And this is actually correspond to genus capital G. Okay, so what objects we will work with? Okay, what we work with, so let's a little bit come back. So what we know on surfaces, you have the notions like a curvature. So you can calculate the curvature, Gaussian curvature, right? And what it is, the Gaussian curvature is kind of the limiting difference between there's much of ways, okay, you can ways, but one of the way to think about is it's the limiting difference between the areas of balls in your metric versus versus like the standard like Euclidean one, right? So let's assume like, so I have M, so I can look at a smooth Riemannian metric, like smooth Riemannian manifold, so that I have a metric, right? So I mean I can write the expression let me clear. So what I mean by limiting, so we need up to some constant so that you get in, but it is that, right? So area G ball around X and R to the fourth. And if you try to calculate for kind of classical examples, I mean, if you actually say take Euclidean plane like balls, right? Exactly pi r squared, you will get 0. Okay, it's a 0 curvature. You can do for the sphere, you can do for constant negative curvature, and you'll be getting exactly the results which we expect for Gaussian curvature if you use the formula. Kind of other definitions as well. But what is known as also about the Gaussian curvature is the way that there is a Gauss-Bonnet theorem, right? Your average of the curvature is equal to the 2 pi chi or 4 pi g minus 1, right? Like your genus. And what we see is that those two examples cannot have curvature g negative everywhere. It's just not possible by the average. So the classes of metrics which that we will be working will be exactly interested in the negative curvature, and that automatically means that this is the objects we'll be working with. Okay, one of the examples you can think about like donut with 2 holes, right? Okay, so this is the class of surfaces we'll be working with. Okay, so as I said, that what we would wanna G, the metric, Riemann metric, have negative curvature. And okay, we have a Riemann automatically G greater or equal than 2. And what we have when we have a Riemann metric, we have a unit tangent bundle. And we have a natural kind of dynamical systems here. We have geodesic flow, right? So which is defined on the unit tangent bundle. So you have a family of diffeomorphisms on here, which kind of base takes. So you have your unit vector, it defines your uniquely geodesic, and you move time t along it. You see what's the tangent vector here, and this is your output, right? So there's naturally this system, and this is basically the class of dynamical systems we will look at. So class of systems. We'll exactly kind of will be looking at we chose geodesic flows on negative curvature, on negatively curved surfaces. Let me kind of rewind. So if there are any questions, please stop or like just unmute yourself and ask, probably the easiest, or somebody tell me that there is in chat if I miss. So let me rewind for. Okay, great. Thank you. Let me kind of rewind a little bit. So this is the class. Let me say something a little more. So we talked about the curvature of negative curvature. So kind of how else we can kind of see that, like say geometrically, before we kind of go to the invariance. Okay, one thing is also to know about the surfaces, and again, this is kind of the dimension 2 thing. So there is a uniformization theorem. So let me, I found it. So let me do uniformization theorem. Uniformization theorem. Okay, what does it tell you? That, okay, if we're looking at the negative curvature, then we always can find a function on M such that G is look like e to the 2u times sigma, where sigma is actually metric of constant curvature. I can specify -1. And also, actually, what is true in in dimension 2 is that actually there is not only one metric of constant curvature -1 on a specific so, but there's a lot, and there's actually so there's a Tuchmiller space of metrics. So let me kind of draw this way. And what this theorem more or less says, which is kind of not fully, but almost looks like over each point in Tuchmiller space, I have a fiber, right? Or function multiplied all other metrics. So I can view it so there are constant curvature metrics, and kind of I can move from one constant curvature to the other. And also there is a fiber I can move so changing the function, right? So kind of more or less like this structure. And kind of sometimes helps to think about. One more thing, kind of saying so where this all kind of constant curvature, because if you think about your surfaces, okay, let me again kind of go to the donut, you kind of can cut it into pair of pans. So for example, say genus 2, I have two pairs of pans right here. And so you have kind of what you have lengths of those curves here, and depending how you glue it, right, which you can start assigning. And actually it's possible to construct this pair of pans, you can assign any numbers you want. You can construct pair of pans, so then and afterwards you can try to glue in the surface and get in your surface. And the thing, if you think what is kind of the boundary of the Tuchmiller space, it's surface have very, very thin neck. And as I learned from Dan Salomon how to draw it, you should draw like this. And he usually was going from one blackboard to another blackboard over and over. So it's very, very thin further you go to the boundary. So this is the example. And you'll see why I'm mentioning it, because to what I'll be going further about flexibility in this setting, those existence of those guys is very important. Okay. So so there's the structure, but okay, so this is kind of geometric what happens. And maybe one more thing to comment about negative curvature, what we have. So we know that my G looks like this, right? And what does it mean for the curvature? So what about Gaussian curvature? And actually the curvatures are also connected. So it's if you take Laplace on this u with respect to sigma, and you subtract the Gaussian curvature of your sigma, okay, -1 if you wanna, it doesn't have to be constant curvature. If you only write this way expression, those type of metrics, saying you're saying basically that G and sigma conformal. So if you have that plus kg e to the 2u, so that's a curvature of G times e to the 2u equal to 0. Okay, and looking at this expression, what you see that the only way to have kg strictly negative, right, it means that your Laplacian of u has to be bigger than k sigma. So in this family of functions which you can take, the only ones which will give you negative curvature everywhere the Laplacian is bigger than whatever sigma, so I say -1, so it's bigger than -1. So it's actually cannot be an arbitrary function. But you always can ask how large that class is and everything specifically. But let me leave it at here so that there's this connection about the conformal classes, and actually go back to the question. So what we did so far, we define a class of systems we want to look at, right? This is our class. So we're looking at the geodesic slope of negative recursive surfaces. So the next step, what you want to ask is what quantities you want to look at, what invariance. Okay. There are several natural invariants which you can pick. You can talk about topological entropy. It's kind of, you can think about this as a global exponential complexity, like how many like distinguishable orbit segments you have. And I believe Karen Butt like talked with you or had the lecture about this. So let me skip. If there are questions, I can go more details. The other thing is there is also Liouville like metric entropy with respect to Liouville measure. Okay. So what is Liouville measure? Liouville measure, it's another measure. Okay, it's another measure which is which lives on a unit tangent bundle, and this kind of comes from the comes from a Riemannian measure, and basically locally looks like area times the measure of the angle. And we always will assume that our measure is normalized so that our measure normalized the way that unit tangent bundle has measure 1. And there's another quantity is what you can, so metric entropy is kind of topological, it's total complexity. Metric entropy, when you look with respect to some measure, it's kind of complexity, but where you're looking for the prism of this measure. So you kind of might be disregarding some stuff, only look at those which are important for this measure. And it's kind of, I think, like Karen gave like you 2 ways of ways definition where it's visible that this disregarding when you're looking at the sets of which are significant for that measure, and basically repeating the definition of topological entropy, which is up. This definition is due to catalog. Okay, so we have those 2 quantities, and let me write one more quantity. I'll call it Kg. I'll call it mean square root curvature. What actually it is, it would be just equal to the integral of the square root of minus Gaussian curvature over M with respect to the Riemannian area. And when I'm writing this, so let me always assume my normalization is such that Riemannian area is always 1. Otherwise, you need to rescale everything like in the further quantities which I write. Okay, so there are these quantities, and let me stop. There are obviously more other invariants which might be interesting, but we will just concentrate for a second on those ones. So from the scheme which I drew you at the beginning, so pick the class, we picked geodesic flows on negative curved surfaces, pick the invariants, we picked those invariants. So the next step, what you can ask, what do we know about them, right? And the answer is the following, that we actually know if G has constant curvature. So if it's actually a matter of constant curvature, then all of those quantities coincide. So the ones which I wrote to you. Okay, I see. It depends. So, for example, topological. So there was question about like invariance respect to what. For example, there is topological conjugacy. So is, for example, there's existence of homeomorphism, so that so say I have my geodesic flow and I have other I have a homeomorphism, so not the same H, but usually, and another flow. This is true, say, for every T. So they're topologically conjugated. So then the quantity topological entropy would be coinciding for those 2 flows. And if for each quantity, it would be like its own kind of class. So kind of measure conjugacy like the one with respect to Liouville, so you should be careful, but they're not invariant under conform. So as we'll see, like I didn't formulate what happens, knowing just that two metrics conform equivalent doesn't guarantee you that any of those quantities is coincide. Or so. I hope I answered the question. If there is further follow-up. Yes, every metric on surface is conformal equivalent to some constant curvatures. As Karen pointed out, it's also true. Yeah. So there are some quantities though, like which I'm not mentioning, which exactly because of this conformal equivalence, they actually would be constant. There's some and entropies are related to the conformal, like which I want. Okay, let me say there's a Kaiman. If you're curious, you can look at the Kaimanovich entropy. So that's a quantity which actually in dimension 2 is constant exactly because of the reason that every metric is conformally equivalent to the metric of constant curvature. But the ones which are talking today, they're not invariant under conformality. Okay, so hope I answered. If there's follow-up. Okay. Since there's no follow-up, so let me continue. If there are more questions, I'll try to answer it as well. So let me, so if we have a constant curvature here, as I said, so we actually know those quantities, all quantities coincide. Sorry, my pen sometimes like doesn't like to write, so. Liouville entropy coincides with topological entropy. And what is equal to it, it's actually would be equal exactly to the 4 pi g minus 1. Okay, when I'm writing this, I'm using the assumption that area g of m is 1. Otherwise, you need like to rescale appropriately. So they all coincide, all those quantities. Basically, they all the complexes kind of the same, like divergence you see like from the curvature behavior and everywhere the same curvature. And using Gauss-Bonnet, you basically understand those quantities have to be square root of minus curvature. And from Gauss-Bonnet, you're exactly getting this expression that is a square root of 4 pi g minus 1. But what happens if g is not, so not metric of constant curvature? Then the following actually holds. So you have this like special number here, which just comes from metric of constant curvature. And that number is strictly less than topological entropy of G. And this number is strictly bigger than Liouville entropy with respect to G. Sorry. G, okay. And this number is strictly bigger than this mean curvature, square root mean curvature. Sorry. Okay, good. Let me write. Right. Okay, that actually all those inequalities are strict, and those two are due Katok, and of his work like of 82. And it basically has, if like you have a quality, you have to be constant curvature. And this one is the inequality itself is due to Manning. And it's kind of actually not written there about, I think it's 81. Let me, if I'm correct. Okay. Yeah, so it's 81, and kind of the rigidity part about if they equal, it has to be a metric of constant curvature. It follows from the the work by Osserman Sarnak of 84. And obviously, I should probably point out that this number is strictly has to be positive. I'm not letting by my computer to write, but it is positive because we have negative curvature. I'm sorry, it's really late. Was okay, negative curvature. Okay, so we have that relation. And so now we kind of in the setting of we have a class, we pick the quantities, and the next thing we learn some relations, and you can ask like, is it all relations that you know? In a sense, are there any other between them which we kind of didn't mark? Maybe actually more is known. And so what the answer is, so let me kind of like in two steps to say. So the theorem due to myself and Anatol Katok, we actually looked only on the entropies. So what we were able to show that so if you fix your favorite genus greater or equal than 2, so it's an all-natural number, and you pick your favorite two numbers, A and B, favorite two numbers bigger than 0, such that A is less than square root of 4 pi g minus 1, exactly that number which separates the entropies, and A and B are separated by this, then I actually can find you a smooth Riemannian metric G, such that I have all the conditions which we've talked about. So I'll have area, total area being 1. I'll have G has negative curvature, meaning at every point it's negative, right? I will have that, and I will have those A and B be not just any numbers, but exactly the entropies. So my Liouville entropy will be exactly A, and my topological entropy would be exactly B. Okay, and okay, so the and maybe let me kind of, then you say like, what about the other quantity? Okay, this is kind of, I can't give you full an answer yet, but kind of work in progress. Hopefully it will be finished. It's actually with one of your mentors that we want to, so it's with myself and Mitsutani, Daniel, that we want to show that actually the triple is also flexible. So K, H Liouville, and H top, Liouville and H top is flexible. It's flexible in the same sense, like, so there's relations which we discussed, and similar like how we did with Katok, like we took numbers which satisfied this relation. We found a Riemannian metric in the class which satisfies the being negative total area, and the numbers are exactly the entropy. So think about that you added one more number, and now you also can realize the curvature. Okay, so this is kind of the flavor of the flexibility results. So then you can ask kind of, how do I show those type of things? So we said that the tools are kind of like perturbation and everything, but how can I come up? So basically the idea also of flexibility that it gives you a way, or makes you makes you concentrate on trying to see what each quantity actually sees. And when you kind of try to estimate Liouville entropy, you kind of might want to ask yourself questions. What like when I move along with geodesic, what do I typically see? What curvature do I typically see? And how often? I mean, I'm a little bit vague, and when the construction comes, like I'll try, like hopefully it will be more clear. But kind of think if you're sitting on a geodesic, and then say, and this is geodesic is the one which Liouville measure like notices what it does, and because all these measures like Liouville and photopologist there's measure of mass, they're kind of forgoing. So you take this like good geodesic and you move it along it, and it says, and you just see like, oh, here I'm traveling, I don't know, like in curvature -1, and I move further. Okay, here I'm curvature 1 -1 million, well, but now I'm almost very close to 0, and this is kind of like varies, but kind of still it's kind of on average kind of like what do you see, right? Like as a total behavior, and so you want to like answer that question, and Liouville is about like this typical geodesic. When you think about the topological entropy, about this quantity, okay, there's like general definition, but another way of convenient thinking about it is that maybe I'll write lower. It's actually coincide with exponential growth rate or volume growth. Or in the kind of all the balls in the universal cover. Universal cover. So you kind of can see this quantity, like you took a ball and you compute the volume and like look what is log of the volume or area, I guess, in dimension 2. If you see divide by like how large your ball is, like the radius of it, where it tends. And it turns out that they coincide. So it's one way of seeing like what happens. Or the other way to see what it is, it's exponential growth rate of the number of closed geodesics. Exponential. So growth of the number of closed geodesics. Okay, the idea, the way like kind of if you have a lot of for all length r, kind of how many geodesics do I have of length less than r, right? And kind of close ones, and then you see, okay, now I'm increasing r, so what happens? How this number grows? I mean, I'm a little kind of close geodesic. You can say more about. You look at the homotopic classes. Each homotopic class a unique representative geodesics in this, and you look how that number grows. Okay, so there's like two perspectives. So you're trying to learn like what matters for this quantity. So for this quantity, so for example, topological entropy, you can say, okay, what matters? Okay, how volumes of the balls, how the balls look like, right? A little bit, or how many geodesics do I have? Or the other one, so the last quantity which we didn't discuss is kg, but it's kind of in a way maybe kind of roughly to say, kind of it's average of the curvature, and it's more or less you can say what is typical curvature, like what is a typical square root of curvature. Okay, not fully right, because we know like you can make integral like the same quantity, but being drastically from that number big and drastic small, but an average will be the same. But for example, if you can realize the examples where you always see the same number, right? Like if your curvature is the same number, then more or less your average is also close to that number, right? So if you made the curvature constant, right? Like constant almost everywhere. So more or less the average would be close to that number. Okay, so in some sense, you kind of can try and analyze the systems in this way. And kind of more or less from this analysis come their like geometrical constructions. And so let me kind of give like what how the approach here and goes results. So first of all, let me constructions and the proof, maybe like I'll call it this way. And proofs. Okay. So kind of like you can start from your any metric, for some reason your favorite one. But sometimes it's easy to kind of start with the ideal guy. And ideal guy in this world becomes like the metric of constant curvature, right? So you can think that you started with your metric of constant curvature, so -1. And I will go the way of making large perturbations. Okay, and say for now I want to say topological entropy first. So let's a little bit kind of maybe simpler in some way. So you want to make it say large, right? So we have this like it's bigger than some number, but I'm saying like it can be arbitrarily large. So how do I make it even bigger? Okay, and we're kind of going back to okay. I even can somehow can see like how the balls become so that the volume gets bigger, or maybe I can talk about lots geodesics. Can I generate a lot of them? And what we can do is that let's try to make more kind of generate more and more closed geodesics, whose length is less than r, right? Okay, how we can try to do that? Oh, we can try to shrink one of the curves, make a little short geodesic. Okay, this one a lot, but like you might say it's not enough, but assume you can do that the way that you really just shrink here, so you kind of don't increase or anything like in the other length, then you actually get a family from different homotopic classes curves, right? Because you can wind around here, go here, and say close up, or you can do like wind around in the other hand, and so on. So you kind of get an actual lot of them. And you actually can make it this precise. Okay, everything sounds good, so I generate a lot of curves. The one the variable view might be, okay, I shrink the thing, right? Did I keep the negative curvature? Because like if you see like if I'll maybe like it's deceptive, but looking like looks like we're creating positive, but it's the case, or maybe can I do it like negative? And if I can I do it like so I want to shrink, and we have this nice bound about like mean curvature here, right? And kind of feels like I'm not changing anything here, I'm not working on this piece. But the question then to make is not really make sure the Liouville entropy doesn't drop, I need to make sure that I'm doing it arbitrary small piece, right? So that the area doesn't change, because remember we're normalizing area always being 1. And the thing happens that actually you cannot do for free. Like if you took your favorite one, you need some room. So need room to keep negative curvature. Then you might start worrying, okay, maybe I'm gaining, but then I'm renormalizing them, I'm losing, right? So I kind of the game. But the thing that this is where it comes this with long necks. I can do this modification maybe with this guy, right? Who had like my long neck. Okay, the bad would be story if I needed a bigger piece for this one to do. But the good news actually, you need a fixed size room to make negative. To make negative curvature and kind of like to make negative curvature and short curve. And it's kind of so it's independent of constant curvature metric. So for each of them, there's like kind of upper bound how large the piece should be. So if you're going further, that piece it's very tiny. So you make a modification, so you're blowing up your topological entropy. But in the sense of metric entropy, you don't change it because you keep everything where almost like -1 curvature, right? Because of this lower bound of by square root of average of the square root. So, and it's kind of here comes what I was trying to say about like what you typically square root curvature you see, right? Typically, I would be seeing very close to -1. Okay, so I hope I convinced you that how you can do like the topological large and the will not change much. So let me a little bit tell you about how the Liouville, about like how often you see, and maybe a little bit comment about the way what happens with kind of the result with Daniel. So now think about, again, you have your favorite guy, constant curvature -1, and all those surfaces you can triangulate. So assume it's triangulated. So, and for now you have curvature -1. But what you can do, you take this triangle of curvature -1 with those sides A, B, C, and you can build a triangle of 0 curvature with the same exactly size ABC. So geodesic triangle, but in Euclidean. What happens that this angle, each angle, so if I have here alpha here with alpha prime becomes bigger than alpha, and it's true for every other. So the angles grow by comparison theorems. But what you do, so you have your surface, you triangulated it, and now you build those other triangles. You can glue them back together in the same order. And what you see that you see 0 curvature. Okay, up to a problem. Okay, we know there is no like 0 curvature matrix on say genus 2 surfaces. Oh, where's the curvature live? Okay, it lives in this exactly like points, like right vertices, because like each angle grew, so you actually get cones of angles. So you're getting cones with angle larger than 2 pi. And kind of you should think like there's these like minus infinity curvatures. And what you can do, you can actually smooth. So at the end, because we talked about smooth matrix, what you can do this way, you can construct matrix which are kind of 0, almost there, but you have bunch of bubbles of very negative curvature. So everywhere 0 curvature with bubbles of negative curvature, very negative, but they're very small. And okay, from the alluvial point of view, what picture you would be see like from the measure, if you take typical geodesic, what you see, you'll be moving in 0 curvature. You have to visit those negative curvature from the ergodicity reasons, you have to. But the thing that you wouldn't have visited that very often, you actually most of the time you will be, for a long time you'll be in a 0 curvature, and then you will bump into, oh sorry, so if you look at the kind of graph of minus curvature, what you see, you bump into very negative curvature, but then you'll go back into 0. Okay, there might be accident, sometimes you might be entered and then again entered, but then it would mean that later you have to spend again a lot of time in a 0 curvature. So here high curvature, like very negative. Okay, so typically it's actually would not but it wasn't, so basically the idea that it wouldn't visit this negative curvature very often, and most of the time it spends in a 0 curvature. And this way, kind of making this analysis carefully, you actually can show that metric entropy does like with respect to alluvial measure does go to 0. So kind of when you squeezing those bubbles. Okay, so this is kind of like second construction, and then you can kind of combine this construction. You can shrink curve, and outside of where you shrink, you can start doing those approximations and decrease it. So this is kind of more or less the idea for the result with Katok. And then where is the Daniel? What's the difference? How we can do that? So you see, like it's kind of about square curvature, and what's important, I said, like not only what curvature mostly you see for alluvial measure, but also kind of how often do you see it, right? And I said when I was explaining to you, like that with these bubbles, it's more or less it depends on 0 curvature, and then it enters like this high negative curvature. What you can do now, so now we concentrated this curvature on a bubble, but think about that. What will happen if you concentrate it not on a bubble, but on a kind of, you can think about an edges, but kind of on one-dimensional like skeleton, right? So kind of like the picture, I mean, we're doing this for the circles, kind of more or less kind of like that you have in here, kind of 0 curvature, zero curvature. Here you have negative, but kind of like that what you see, like you're concentrating not on the bubbles, but more one-dimensional skeleton. So concentrate curvature on one-dimensional skeleton. So here, this curvature is kind of concentrating here on zero-dimensional, right? It's kind of on the points. This occurs skeleton. So curvature. But here we do the other way. So what was the picture? You cannot go to zero to another zero curvature without vision. So your picture for square root of minus Gaussian curvature becomes 0, high, 0, high, 0, high. Roughly, let me, like kind of like this. And this kind of actually affects a lot of the metric entropy because you kind of don't have time. So in the previous time, when you were spending a lot of time in a zero curvature, you were kind of losing all the expansion which we gain in along the while we move. But here you don't have enough time to kind of lose enough so that you kind of decrease. So because you kind of keep bumping back and forth. I mean, you have to be really careful work through here, but the idea you can do that, and this is more or less, but we'll show that, at least I hope I can convince you that metric entry can be positive, but the square root of curvature will still go to 0, right? Because you kind of concentrate in one-dimensional skeleton, right? And because the square root of curvature, you actually can make this quantity arbitrarily small. So you kind of can separate this way metric entropy from the average of the square root of curvature, because on average, it will be very close to 0. And kind of working through this like geometry, then you need to work through and like write estimates, and it all works out. And maybe I'll finish on the way so you can ask the next questions. Like there's also a lot of open questions, like you saw that I said that when we did this like shrinking construction, I used this models of hyperbolic surfaces, the ones which were very thin neck, right? Like the one with constant curvature. What if we fix conformal class? So what if we look on the metrics, which so we picked our favorite a -1 metric. And okay, and we say we only look at the metrics which are multiples of this. So you remember we had this kind of relation between the curvatures. So if we want to have negative curvature, let me like kind of negative curvature, I have this relation, right? But so I'm allowed to take in functions like this, multiply my metric, and say what I can realize. And actually, in this direction was some partial progress of Thomas Bartholomew and myself. We actually showed that topological entropy no longer can go to plus infinity. So this way, like that I said to you, that we have to go to those examples and then shrink, kind of was very important. So otherwise you cannot do it. So there's upper bound, but there's still a lot of open question about what is upper bound and what actually can you realize in the fixed conformal class. So still a lot of open question. And obviously a natural question, what if dimension is bigger than 2? What do you have there? And it's still quite open. The reason also like that there is less more known, like in a sense, like there's no like precise bound. So we actually know that there's no analog. Okay, there is one analog. Okay, there is something like the topological entropy cannot drop than a specific number. There is an analog of the Poisson-Courtot-Galois theorems, but the way that Liouville measure is like smaller than specific number, this part is no longer true. There is examples by Flaminio where you can increase. There are ideal guys in higher dimension with which you can start working, but there you can increase beyond that number. So there's a lot of question how large it can be, and obviously the open. There's analog of the square root mean curvature, there's actual rigidity results in that part. And so you can ask all of those questions, and it's quite open. So what is possible is no. So there's a lot of interesting questions, and obviously you can throw in kind of other quantities, other invariants. So what can you say about them? And there's plenty of work, so if somebody interested, they obviously can find a problem for them to work on. And I'll probably stop here. Thank you very much.
Well, thank you for a great talk. Does anybody have any questions? Either unmute or type them in the chat.
So I'm still a little, I have a follow-up question to ask on the question I asked earlier. I do believe that these are invariants under topological conjugacy, like the measure in topological entropy, but you write them as functions of the metric.
Right.
Yeah, and is there any kind of like what classes of metric have the same like these invariants? Like are these invariants of some equivalence relation on these metrics?
Like with respect, I mean, it's a good, you can add like to the big, it's a good question in a way, like, and I don't know the answer. You can ask like, okay, I look at all metrics, right? Like I look at the set of the metrics so that topological entropy, I don't know, my favorite number, A, right? What is it? So if you wanna like in this regards, and I don't know the answer. Like, can you describe all those metrics? And it would be very interesting. What is the set? So what specific happens with those metrics? And it's quite open. So how large it is. From the construction, I can tell that there's definitely not kind of, there's this also even like, you see like even like, so all those metrics of constant curvature, right? They all sit here. So that we know, like that point, which is square root of 4 pi g minus 1, square root of 4 pi g minus 1, right? That point, so it's my metric entropy picture. So it's my Liouville. Here's my topological entropy, right? Say, assume only those two quantities. So I do know that that point is only realized, so they sit only constant curvature, but I know there's the whole modular space, there's a lot of them. So I can describe you that point. But if you ask me any other point here, even like, so this was probably a bigger question, but say even both of them fix them, and you ask me what metrics have that pair, I don't know. I can construct you an example, but I don't know like how large it is. I know it's not unique, but I don't know like how many there. Yes, if somebody can answer that, would be great.
Yeah, I have a comment about this question. Just something much simpler. Just I don't remember what the exact question was, but it was something about like, basically the geodesic flow is a flow on the unit tangent bundle, and we're talking about all these dynamical things, and just asking how this flow on the unit tangent bundle relates to the metric on the surface is just a very subtle question. And like in general, metric entropy won't be invariant under topological conjugacy, but it's a deep theorem, Mark length spectrum rigidity, that if your geodesic flows are conjugate, the only way that can happen is if the metrics are the same. So then everything will be the same. But that's hard.
Are there any other questions?
Oh, I guess I'll ask another question. Wait, hold on. Let me turn on my video, see if I can ask this properly. There we go. Hello.
Hello.
So my question was kind of following up on this question about how you can identify how I don't know if I should use the word flexible here because that's loaded, but you know how much leeway you have in terms of picking different topological entropies while trying to keep the Liouville or metric entropy the same.
Mhm.
And I wonder if this could be a question to ask about how many metrizable topologies you can give the space that generate, because you could ask the question of like how many metrics generate the same topology, and then you know you can answer it that way. But I think that there's another avenue, which is, you know, what are the different topologies that you can generate from metrics on that space, and then see whether or not you can analyze the topology of those things. And the reason that I think that that's interesting is because whenever you have a compact metric space, you have a lot of, like, you can't alter the topology without either losing, you know, Hausdorffness or compactness, which are like big things that you wind up caring about in these spaces. So my question is, like, does it make sense to look at it from a topological perspective? Or do you really need to make sure that you know you have your like metric, you have that bilinear function, and you can't just say, okay, let's just consider metrizable instead of metric?
I mean, like, I didn't thought much about this, but like for like immediate like reaction. So, okay, topological entropy invariance. So if you take different metrics but which generate the same topology,
Yeah.
obviously it's that's why we call it a topological entropy, and because if they generate different metrics which generate the same topology, you still get the same number.
Mm-hmm.
So which is reasonable then. So it's kind of not as a sign, although like if you're probably Karen gave a definition there, you kind of do use the metric. So in that sense, it's kind of, I guess it does make sense to ask like, what if you look at the different, because you can give also topological entropy definition using really open sets and everything. And
Right.
I didn't thought about much, maybe if somebody on audience, about like if you use different topologies, what answers you get. I think it's interesting would be just to see, but I didn't see anyone like actually doing it.
Nope.
Because there's always like natural topology, right? There's like
Right.
Riemannian metric, and this natural, and people work with that one.
Yeah.
All the definition, but yeah. So would be good. I don't know if it would be like kind of nice answer, or maybe it doesn't make not as interesting. So I don't know, like worth to try.
Yep. Thank you.
I am muted. I'm talking to myself. Okay, well, let's thank Alena again for a great talk.
Thank you.